My name is Evgeniy Muralev. I am Senior Software Engineer at Spirasoft, and I give this talk with my colleague Mark Vince, who is Senior Rendering Engineer on my team. And in this talk, we'll discuss fragility of optimizations done by the compilers, and also we'll look at some of the general ideas, how to write code which fits modern CPU microarchitecture, and ways of optimizing algorithms respecting modern CPU. Small disclaimer, this talk contains some assembly code and low-level material, and we will focus on compilation for x86 and associated CPUs, but the general advice should be applicable to wider range of instruction sets and architectures. Before we actually start, just a quick poll. How many of you guys working in games industry? Okay. Okay, not many. Yeah, it's good as I expected. Perhaps we learned something new about it. So, developing AAA titles, we do care much about performance. For example, if you're making a game which runs 60 FPS, you have 60 milliseconds per frame to update the frame, and there is a lot of computational intensive stuff going on, both on the CPU side and the GPU side. So we will focus on the CPU in this talk. And going to the compilers, there are roughly two extremes of thinking about compilers in terms of optimizing your code. The first extreme is like, oh, compilers are terrible. I just write in assembly, which of course is not always feasible. Second extreme is like, yeah, compiler will do everything for me, so I really shouldn't care about underlying performance of my code. In reality, neither extreme is quite true, so we're somewhere on the middle ground. And looking at the last couple of decades, compilers have become increasingly smart. They perform a lot of smart tricks. We have link time optimization. They do loop unrolling, etc., etc. However, there is great danger in assuming that the compiler will do all the work for you. Because in practice, compiler is limited to really small optimization space because it doesn't know all the data constraints which you have in your program. And also, it may not be fully aware of underlying CPU microarchitecture for some practical reasons. And I hope you'll be able to demonstrate this in this talk. And now, imagine you're performing some computation with integers. And for example, if you know that one number lies in a certain range, you often can perform a lot of optimizations based on this data. So how you can specify the range of the variable in the C++? Yeah, just definitely use a type like int8, so you basically just have 1 byte to represent number. Obviously, it has a restricted range. Or you can use a bit fields, or you can deduce it from a source program. For example, if you have an if block, it's obvious that variable a is in limited range from 0 to 100. And it also can be deduced from the logic floor. It's also obvious that in the last expression, a is in the limited range, right? Oh, sorry. Nope. Far away. What's up? Oh yeah, okay. Imagine you have this function, right? Diff test, pretty simple. It's very obvious that after this expression, n lies in range from 0 to k. And it's equally obvious that the result of the division will be 0 or 1, and it will be 1 only if n equals to k. By the way, is everybody familiar with conditional set move instructions? Okay, in case you're wondering, the set equal instruction sets the value of register to 1 only if the previous comparison sets equality flag. Otherwise, it just internally converted to no operations and nothing happens. But obvious for this division, you don't actually need to perform division. You can substitute this simple assembly for it. But okay, let's see what the compilers do for us. And the both compilers actually do perform the division. It's about GCC and the MSVC compiler with all optimizations turned on. But you don't need to do this division. And what's important here is that the division of integers is very expensive operation on modern CPUs. It can take up to 30 cycles or even more. But you don't need to do this. It's like the first fail case of the compilers where they can't deduce all the data restrictions from your source code. Okay, let's say we specify a range of the variable by using some conditional flow instructions. And again, like it's pretty obvious that the result of this division will always be 0, right? And let's see what the compilers do. The GCC is pretty smart. It's able to recognize that the result of this function is always 0, so it basically just returns 0. Guess what MSVC shows us? Oh, is this? Like, yeah, everybody knows how it refers to division. No? Okay, we'll look at this trick a little bit later. So let's complicate example a little bit. Imagine we return 1 in case we don't go to the if block. And we see if, check if the compiler is able to optimize this away. Yeah, I mean, it made no sense to show output of MSVC. It's still very bad. But the GC is again smart. It uses conditional set instructions. So it's pretty smart to recognize that you don't need to perform any kind of division here. So again, okay, let's make it even more complicated. And now, in this if block, n can actually be equal to 123. So the result of this division, again, can be 1 if n equals to 123. And in this case, you expect basically the same piece of code, because this result of this function is identical to the function on the previous slide. But it did this minor change, and even GCC fails to optimize this away. You see, it generates again the same piece of code. So yeah, looking at this specific trick, division by constant can be replaced by multiplication and right shift. And these values can be computed statically for multiplication and right shift. If you want more details, I really encourage you to check out Hacker's Delight book. It contains very definite explanation of this trick and many others. However, these generated numbers are for any 32-bit values, which value can take, but we know that n is in a restricted range. Okay, just a little bit simpler example. In this block, again, it's obvious n lies in range from 0 to 40, and we divide it by 10. So GCC generates this piece of code, but if you assume that n lies in this range, you actually don't need to use these big numbers for multiplication and right shift. We just computed it statically beforehand. You can actually replace it with 26 and 8. And if the compiler was able to recognize this, it could perhaps generate a code with less register usage, with more opportunities for optimization and vectorization. Yeah, by the way, we'll discuss vectorization a little bit right now. Remember single instruction, multiple data? Are you familiar with the vector registers on a CPU? Okay, basically, all modern CPUs has a wide vector registers, like XMM registers, which are 128 bits wide. And basically, for example, you can perform 4 floating point additions in a single instruction. Every operation is being performed in this, in its 32-bit chunk of this wide register. And even scalar, floating point additions, are being performed in these wide registers, but you are just wasting the other bits that you have in this register. And the modern microarchitectures, they even have wider registers like YMM, ZMM registers, which are 256 and 512-bit wide, respectively. So, and yeah, that computation in these vector registers is being supported by SSE and AVX instruction set extensions. Actually, there are a lot of processor-specific extensions. And if you're wondering about hardware support, SSE is pretty old. And for example, SSE2 is pretty valuable target. And it came out in 2001. So you can definitely expect that your target processor will support these instructions. So just simple example, you have a vector4 class. It's pretty straightforward implementation, but it's just for the sake of example. And you define operator plus. So this is how Scala code looks like, where basically in each block is pretty much identical. You just compute respective additions. And the vectorized code looks like this. So you use a single add-pass instructions which perform the four floating point additions at the same time. So let's see if the compilers can actually utilize these vector registers, because obviously the code is smaller and it's faster. So if you have this simple loop, which calls a do something function on every element of array, basically we perform the addition across all elements of this array. And do something function is definitely in line right here. And they compile it. The GCC is very smart. This is our loop in assembly, and it uses packed add instructions. So basically, this guy performs 4 integer additions at the same time in this vector register. And you see the offset to the next iteration is 16 bytes. So you're basically offsetting like 4 integers in a single operation, in single iteration. So yeah, that's pretty smart. And if you're wondering what the rest of the code is doing, that at the end of the loop, you have 4 partial sums, and it just performs summation across registers, so you get a final sum. Yeah, if you're worrying about the code size increase, you should note that the size of the critical loop is still very small. Yeah, the Microsoft is also smart. It vectorizes code, and based on its some internal heuristics, it does 2x loop unrolling. Yeah, it just loves unrolling for some reason. Okay, so what can go wrong? What should really bother with these vector registers if the compiler does it for me? Okay, let's say we have some changed requirements, and we changed our variable type to floating point. And we get this. Oops. Something. Yeah, it's something wrong with the. Yeah, something wrong with the clicker. Okay, so you get a Scala addition for here. So basically, it doesn't utilize all lengths of the vector register, and it performs a single addition in the iteration. Does anybody have any ideas why compiler didn't vectorize this code?
Because you cannot reorder summation of floating points because it leads to a different result. You need to enable fast math to
Yeah, exactly. The reason for this is that the floating point math is not associative. And so because of the round-off row, you could get a little bit different results. You probably don't care about it, in most cases, but still, this is what happens. And it just kind of shows how fragile these optimizations are. Yeah, it's easily fixed with fastmath flag. So now it does perform the vectorization for this piece of code. Okay, by the way, again, the compiler doesn't know all the context for your target processor and that kind of stuff. So if you know, for example, you're developing some application which runs on some server cluster which has hustle CPUs, let the compiler know about it if you can. Because if you just pass this microarchitecture hustle flag, the compiler can make assumptions that your target architecture will be at least this level, and it can perform even smarter optimizations. Right now it uses 256 byte registers. So basically, as soon as you let the compiler know that the target architecture supports it, it's able to use even wider registers and perform 8 additions per iteration. And again, look at this same example. Imagine this do something function. We just decided to put a separate library. And yeah, we marked it as external, and it's just defined somewhere else. And you get into trouble because it breaks all kind of optimizations, unless you have a link time optimization turned on. But if you're building dynamic library, you're still doomed. And the problem here is that you're not just paying for extra function call. You kind of cut the function from the context. It's not able to do any kind of optimizations in this loop. And also, you lose vectorization, and other potential optimizations. So it's not just extra function call. Before Mark will continue with algorithmic optimizations, just one topic to remember, the RISC and CISC architectures. The RISC stands for Reduced Instruction Set Computing, and CISC Complex Instruction Set Computing. The difference between them is kind of blurry, but basically, RISC has a simple instruction addressing mode. It has a uniform instruction format. Usually, instructions are being executed with the same latencies, and they of the same widths, and they're simple to decode, that kind of stuff. And you also have a fewer data types in hardware. But as a result, you have a larger semantic gap between high-level program and the underlying instruction set. So it simplifies hardware a lot. And if you look at the x86, it's very complex instruction set. It has instructions of variable lengths, and they execute it with very different latencies. But what's important to know is that underlying CPU works in a RISC fashion, because all instructions are being dispatched to micro-operations. So for example, add instruction where the source operand comes from memory is being dispatched to two micro-operations internally. One loads from memory, and the second one performs addition. And the push AX instruction also being dispatched to two micro-operations. One is subtracting a stack pointer, and the second one, we just store the result into memory. It also reduces data dependencies, at which I'll look a few slides later. So this is a Sandy Bridge architecture. And here you have a processor front end. The front end fetches and decodes instructions. And all of that happens in order, as it's written in your assembly. Okay, almost, because it can actually decode a few instructions simultaneously, but we're not going to go deep into the details. So, but if you look like below, you have really many LEU units. You have load and store units, multiple execution units. So, and that's an important thing to know, because when people talk about parallelism, they usually mean like multi-threading, running the program on the multiple cores, that kind of stuff. But they often forget about the instruction level parallelism. So what it means is that you can execute multiple instructions at the same time, and all that it happens out of order. So if I have two additions going one after another, you can basically compute them in parallel. It's being serialized later to conform memory consistency requirements. But there are two conditions for operations to be executed out of order. The first one is that you have enough execution units, obviously. And the second one, you don't have data dependencies between operations. So talking about data dependencies, imagine you have this loop. It looks like pretty simple, elegant, and probably efficient. But in fact, this kind of loop can perform pretty badly on modern CPUs, because each iteration has a dependency on the previous iteration, and you can't execute them in parallel because they're dependent on each other. So you fail to utilize all LEU units which you have in your CPU. So, and the data dependency kill out of order execution. Your CPU just staying idle. So, but there is a small pitfall here. For example, look at this loop. Obviously, it doesn't have data dependencies between multiple iterations. But the programmer can look at the disassembly and are using the same registers every iteration. So are they actually, data dependent? In fact, it's not, because what we're seeing here is called the false dependencies. And okay, imagine you can compute dot product. And here you're using the XML1 register in add instruction and the move instruction next. But if you really look at this, the move instruction doesn't care about the value which XML1 register contains before its execution. So you're basically just dependent on the name of the register. And when you write to the register after write to it or write after it, it's called the false dependencies, because you don't have true dependencies on the data flow. And the register renaming will eliminate both of these dependencies for you in underlying hardware. So the thing is that, for example, in a Haswell CPU, you have like hundreds of the physical registers. And what happens here, what register renaming basically does, is that in the blocks B1 and B2, XML1 register will actually point to different physical locations. So they're not truly dependent, and you should just bear that in mind when analyzing underlying CPU assembly code. That happens because we have a lot of physical registers, but limited number of registers in our instruction set, and it has certain trade-offs why it's done so. Yeah, we're not going to go deep into the details on this topic. And just bringing the small recap of my sections, it's just important to remember that the compilers will not all solve the problems for you, and the optimizations they do can magically break, so you should be very careful. Also, what's important to bear in mind is that even the single-threaded program is being executed, kind of in parallel. So instructions are executed out of order, and that they're being blocked by real dependencies. And you have false dependencies, basically dependencies on the name of the registers in assembly code. Usually, register renaming will eliminate this kind of dependencies for you. And if the code looks, really simple and elegant, it doesn't mean that it'll execute fast. You should always bear in mind how your underlying CPU works. Yeah, I guess on this slide, my section is over. Thanks for listening, and the Mark will continue with more algorithmic optimizations. Thanks.
Hi, my name is Mark Vince. I am the senior rendering engineer for Sperasoft in St. Petersburg. And what I'm now going to do is to pick up on what Evgeniy was just talking to you about. I'm going to look at this at a slightly higher level in the code. I just need to work out how this thing works. Okay, so what I'm actually going to do here is just start off with some very, very basic stuff. Okay, and I'm going to look at particularly what I call discrete frames and iterative frames as a distinction. So we have a very, very simple loop in kind of pseudocode here. Each frame is totally independent of any other frame, so it's intrinsically parallelizable. Sorry. Yeah, it's intrinsically parallelizable. With iterative frame, basically one frame's input is dependent on the output of other frames, usually previous frames. Well, always previous frames, basically, unless we recurse. So bearing that in mind, and I'm going to, again, pick up on what Evgeniy was saying about vectorization, particularly in relation to SIMD. In the ideal world, when we compile something, we want to let the compiler, vectorize this so that we're doing either 4 or 8 iterations of the loop, in parallel in the instructions. But unfortunately, it's really easy to break this. Particularly if you're doing more complex loops, there are a whole area and a whole lot of things which will cause, the compiler to, not to vectorize. And the general thing I find here, because I do have to check the assembler that I'm producing a lot, because I'm working with quite often at quite a low level, to make sure that the compiler is actually producing what I think it's producing. So yeah, the two main areas which I'm going to look at is basically frame dependency and data collision, but I'm only going to skip over data collision because there isn't enough time to go into this in any depth. And I'm going to concentrate purely on frame dependency. And, okay. I'll also add a little note here on AVX 512, the new kind of, the new SIMD development, available in Knights Landing, Xeon Phi, high-end chips. Just as a kind, I'm not going to go into this in any depth at all, but with AVX 512, it tries to address both of these issues in ways that are kind of transparent to the C++ programmer, for instance. Yeah, there were special instructions basically for both of these things, and this is done in a way that that a compiler which will support this has a chance to try and do this vectorization for you, because if you have to try and work these things out by hand, there's a lot of work involved. Yeah, conflict detection. When I talk about conflict detection, I'm basically talking about, for instance, writing to an output to a container or something, and where you don't know the uniqueness of the indexes. And it's essentially a very nice idea. Basically, you for instance, build an array of 8 indices, and there's an instruction which will give you an indication of the uniqueness of each. But as I say, I don't really want to go into this, basically, because it's not the main topic here. Yeah, I want to look at how the dependencies between the frames break optimizations, how we can get around these problems. I'm going to look at one type of optimization, which is a pretty good example here, which is basically iterative optimizations of polynomials. It doesn't really matter what we look at. It's just an example. It's something that works and hopefully demonstrates what I want to illustrate. And then I'm going to end by looking at a few mathematical relationships, which we can use to get around some difficult functions mathematically. Okay, so let's start with a very, very simple loop. I mean, this is kind of written as simple as I can probably manage to do it. Just simply for adding some squares, summing up squares. Now, this loop is obviously, each frame, is independent. So, the compiler has every opportunity to vectorize this. And I'm also going to ignore the fact that equations of this form have closed form solutions. It doesn't matter, not for these examples. If I skip to the next frame here, okay, is an equivalent function to this, and what we're doing here, oh God, what's happened here? I was trying to look for the laser thing on here actually, to be honest, but okay. What this is doing, it's calculating the sum of the squares, but it's doing it iteratively, okay? There's no multiplication, but in here we have just two additions, but each frame here is totally dependent on the previous one and contains dependencies actually within the frame itself. And this blocks vectorization. So, and this is the code we get. What I've done here is I've omitted a lot of code and just concentrated on the main loop, because in the main loop, this is actually vectorized, and it's actually essentially it's doing two multiplications here and two multiplications here, 32 by 32 to 64 bits, and then it's doing a bit of shuffling and packing here in SIMD. But the iterative form, it can't vectorize this, so we get this really small loop, but it's doing it one at a time, using scalar instructions. And the question is, which is actually going to be faster? And there's also another condition here as well. I mean, we're assuming we're using full 32-bit values going to 64-bit multipliers. We're doing two at a time. And it's like Evgeniy was saying about ranges. If we could say to the compiler, I don't know, the result is always, I don't know, less than, say, 16 bits or something. We could say, I don't know, use a p-mul-h derivative instruction or something, and just get rid of the high parts, and reduce the instruction count again. Okay, so I'll skip on here. Basically, when you're vectorizing the code, you will end up inevitably with a bigger code footprint as well. And we can divide this up into a kind of initial setup code, the main loop, the critical loop, and tail code at the end. And the tail code is typically processing all the little bits that are left. I mean, if I'm processing, I don't know, 70 elements at 8 bytes per time, it's going to have 2 left over, which it has to deal with at the end. So that, but the real main concern is obviously the main loop, because that's the critical one, unless the loop's very small. Yeah, and we also have to be very aware with the vectorization that that any functions which are called when we're trying to vectorize are visible to the compiler at that point. For instance, if we're calling a function in the DLL, it doesn't know what to do with this. It can't optimize this out properly at this stage. We tend to use link time optimization, whole program optimization, that is, because although the footprint's bigger, it actually produces much faster code, because it can see inside the functions it's calling. quite often and make use of that. Okay. So how do we get around a loop which can't be vectorized because of its iteration? What are we going to do here is use strip mining. I don't know if anybody's familiar with this technique for loop optimization. Okay, what you do, actually, this microphone. Actually, yeah, what you do with, okay, what you do here is you essentially break up the range of values you're using into several sub-ranges. And you execute all of those in parallel within the loop. So you don't get rid of the dependencies in each of the ranges, but what you do is you still manage to utilize SIMD, okay? So basically, if we're doing a sum of squares, we can break this into, for instance, 4 equal blocks from 1 to 100, execute the 4 in parallel and just SIMD pack them at the end. Okay. So I'll come back to this in a moment. The initial values. If you're going to break something up into subranges, then you need to be able to calculate the initial value of that subrange. Now, for functions like this, quite easy, but more complicated things, this may not be so easy to do. So here, we're going to do the same. This is an iterative form for a range. And if I skip to the next slide, and I've omitted a lot of code because it's just too much, but it's fairly obvious that we're just doing the same thing 4 times and adding them up and returning the result. However, this does not vectorize. And when we look at the code, realize that the reason it doesn't vectorize is we're adding the 4 components actually within the loop to a single scalar result. And when I tend to use Godbolt or something. I don't know if anybody uses Godbolt to test compilers, but we look at this and say, well, why does it vectorize? And the answer is simple. We just have to hold partial results within the loop, and then sum them at the end, and it will vectorize to SIMD. Basically, it's just this change. Okay, so a little quick summary so far is that, optimization of discrete loops, adding dependencies, we can break them up using strip mining. Sometimes we may need to take another approach, and use kind of SIMD intrinsics, such as the Intel intrinsics library. And this is really applicable because quite often we can get quite complex functions where the iterative solution appears to be a lot faster, but it's not necessarily the case. And I'm just adding a note here about iterative floating point stuff because exactly what Evgeniy was saying about the non-associativity of floating point and stuff like this. We have these problems and we have cumulative error problems as well when we're trying to do an iterative optimization of a floating point mathematical function over a range. And this also affects certain kind of well-known classical optimizations. Probably one of the most obvious ones a lot of people might be familiar with is kind of calculating sine and cos iteratively over a range of angles of constant distance between the angles. Classically there's a very simple optimization which uses trig identities, which enables us, I think, to calculate, with 1 or 2 additions per loop cycle or something, a couple of additions, I think. But this is not only introducing problems with accuracy, it's also, going to introduce dependencies. And, particularly in modern process, you start to ask, is this actually worth it? But what I'm going to do is to look at a specific example here. We're just going to take basically how to kind of optimize a polynomial into its iterative form. Now, if you have a polynomial such as this, a straightforward cubic, then you know, we can always calculate each term of this across a range, you know, with 1 plus the highest power number of additions. So for a cubic, it'll always take 4 additions. With a degree 4 polynomial, you will always take 5 additions, and so on. And when we do the code for this, it looks so much simpler. But what I'm trying to say here is it may not necessarily be faster, you know. I mean, this idea with the polynomial is a very old idea, which dates back to, well, the late 18th and early 19th centuries. I mean, you know, they spent like 100 years trying to build machines to do this mechanically. But basically, we simply take a polynomial and we take the difference between this and the next term, and we result in a polynomial of 1 degree lower. And we repeat this process, and we end up with a series of polynomials which reduces to a constant. Okay? I hope everybody's okay with this. If we demonstrate this, for instance, if I am, again, just looking at squares, you know, if I have a range of squares, 2, 3, 4, that 5 should be in red, by the way, as should this number 9. If I take these squares, 4, 9, and 16, I take the difference, 5, 7, and I take the difference again, is 2. I can then add these values up. 2 plus 7 is 9, 9 plus 16 is 25. I get the next number in the sequence, okay? And if we put this into a loop, you know, we get something like this. This loop, A plus, we put the initial values A, B, C, 4, 5, 2, this column over here. And every iteration of the loop is producing the appropriate results. So it looks like it's going to be faster. This, by the way, is the first attempt to do something like this. In the 19th century, they actually built mechanical machines to try and do this kind of stuff. I think this one is from about 1850s. So, yeah, we definitely don't want to go down that route. Okay, back to this cubic polynomial. We have a discrete way of doing it, very, very simply like this. The compiler, I don't know if anybody's familiar with this, but you know, it will do a certain amount of optimization on this using shifts and adds. It's quite straightforward. You know, the compiler is not going to produce, you know, 5 or 6 multiplications, not for this. But obviously, you know, the actual number of multiplications, sorry, the number of shifts and adds is obviously going to be dependent upon the size of the coefficients. Now this, I kind of knocked this up on paper, so I hope it's correct. This is an iterative form for evaluating this function. And here's our 4 additions for the cubic. The interesting thing here is that we can evaluate any cubic like this. We just need a different set of starting values, which need to be pre-computed. Okay, but again, dependencies, dependencies, dependencies. Right, actually, what I'm actually going to do in a moment is to move on from this, because you know, the only real way of checking this is to actually check what you're getting and, you know, just profile it basically. Because, you know, the actual improvement that you're going to get from SIMD vectorization is typically orders of magnitude greater than this. You know, so unless you have really big functions and difficult functions, you know, there's a very, very good chance that what looks like an optimization is not optimal, is actually slower. And the other thing I want to look at, which has been relevant, is basically the use of basic modular arithmetic to evaluate certain kinds of problems. Particularly where the range of intermediate values goes outside the word lengths capabilities of the CPU. And what I'm going to do is to look at just a couple of techniques and the types of problem we're talking about. Okay, I mean, if we have a simple problem like this, like r equals a times b divided by c, for instance, we know that the total result will be, within the word length of the machine, but a times b may be outside. But this itself is not a problem because all CPUs typically produce a kind of double word output from the multiply and typically take a double word input into the division. So, you don't have to worry about this normally. But there are many examples. I mean, working in the games industry, for instance, you may have, for instance, a character in a big open world environment, which is moving along fixed tracks over periods of time. And all of a sudden, you need to know where it is, a week, say on I don't know, an MMO or something, where the character, say this has been running for a week and you suddenly need to know its exact position. So you tend to find, you can get problems where you have large numbers, mod some other number. For instance, the period of the time it takes to go through a whole orbit of a cycle or something. And this kind of function is also applicable to certain other areas and certain other kinds of computing as well. And so if we just look at this problem here, we have the modular exponentiation problem, the a to the power of b mod c, and we'll restrict ourselves just to positive integers here. We know that the result must be within this interval 0 to c minus 1, but the intermediate result, a to the power of b, may be absolutely massive. Okay, so how do we actually tackle this? Well, there's a few things we can actually do rather than actually trying to calculate this out. And I'm not interested in taking logs and doing floating point stuff here. I want to keep it within the integer domain. So the first thing basically that we'll do is simply reduce the power as much as we can. And then the interesting part comes in, where we're going to take a couple of relationships from modular arithmetic to show how we can do this in a loop, staying within the word length of the machine. Okay, a bit of maths. This is the really important thing here, right? If we have a to the b mod c, we can actually reduce the power by taking the modulus with a totient function. And if there's the totient function, basically is the product of, is the original number multiplied by the product of 1 minus 1 over p for all the prime factors of the denominator, okay? Yeah, it's a bit of a, you don't really need to know about what it is, it's just something that you can use. For instance, the totient function of 100 is actually 40, because 100 is 2 squared, 5 squared, etc. So we can basically form a table of pre-calculated totient functions. And if we skip here, here's an example, 5, 6, 7 to the power 1, 2, 3 mod 100. And I took logs earlier, and I think it has about 1,126 bits in the intermediate value. So for obvious reasons, we don't want to calculate that. So if we just reduce it with the totient function, we actually find it's exactly the same as 567 cubed mod 100. Okay? So we've got something that's far easier to calculate. But it may still be the case that with certain numbers and certain denominators, you can still have something which is still very, very big. Okay, so before I go any further with this, I want to introduce two relationships from modular arithmetic, both of which enable us to tackle a whole family of difficult problems here. Basically, if you have three integers a, b, c, okay, we can do this, the multiplicative form and the additive one here. These enable us to break things up and compute them over smaller ranges. There's a whole lot of stuff you can do working from these. So what I want to do now is to try and bear this in mind, and we'll go back to this original function, a to the b mod c. And the reason, I'll repeat that the reason I'm using this function is purely to demonstrate how, you can break things, you can break up these complex problems, because these are the kind of problems which we do actually come across in certain circumstances. So if we imagine we have a to the, I've used p here actually, yeah. We break a particular power of p, we just break it into its individual component bits. So, okay, so the A21 mod C is A16, A4, A1, all mod C. Then we use these other relationships, the two relationships I put up before. We can calculate that if a to the, well, we calculate this, basically that a to the 2n mod c can be computed in terms of a to the n mod c, okay? So this immediately says I can do this in a loop, iteratively. And here's some code. This is not robust. It's not even good code, to be honest. But it's purely to demonstrate how this is actually evaluated. What we're doing here, we're iteratively calculating this once per bit. And wherever the bit is set, we are combining it using one of the other, using the first relationship, the multiplicative one. Okay, and at the end of this loop, we actually get a to the power of b mod c. There's a couple of things I don't actually like with this, the fact that we have a modulus here and a mod here, which of course means calling a division operation. And we can actually get rid of that in the following way. We can improve this. What we can do, we can effectively, we only need to take the mod when the result will go out of range. And I'm not going to prove this. Just accept this. It is the case. But yeah, the value I've put for max root is basically, I call it max root because it's the biggest number such that, for instance, here a times a will go out of range. So basically, if a squared is going to go out of range, we reduce it at this point. And finally, we check and do a possible final mod. Okay. Now, this is the interesting thing. With a loop like this, we have lots of dependencies, which are both inside and outside the loop. And if we do need to calculate these kind of functions, then we, again, end up with the same problems of vectorization. Also, this particular kind of function does not easily lend itself to strip mining because we don't know the whole state of the frame at any particular point without evaluating it to that point. But this actually opens up a whole class of algorithms for doing these kind of things where you get huge intermediate results and the final result is going to be within a smaller range. And also there's many ways to improve this as well. And I'm not even going to attempt to go into this at the moment. Current areas of research are into things like non-adjacent format numbers, different ways of counting and mapping, and there's really complicated stuff being done, which is basically driven by the kind of cryptography community. And I'm just going to end by giving another example, which is a simpler example. We can compute b mod c without doing a division and using a right to left algorithm. When I say right to left, I mean least significant bit to most significant bit, because obviously, once we start juggling around with bits, we're going to end up with, if we're not very, very careful, with kind of CPU-specific code and all the rest of it. But because we work from right to left across the bits, this implies that we can do this for any size integer we want. There's no real restriction. We don't have to use just one word, because we're not looking most to least. We're looking smallest to biggest. And again, this comes out as something like this. Again, we end up with a loop. We end up doing a bit mask test to see if the bit is set, accumulating a result, and at every potential bit, we are keeping the mod 2 to the power of however many iterations. Okay, so this loop looks very, very similar to the other one. It's just not as complicated. We don't have to deal with the multiplications. And yeah, just a quick recap then. What we've been talking about. Evgeniy was speaking, particularly about instruction level parallelism and getting vectorization using SIMD, and also, about avoiding false dependencies at the CPU level. What I hope I've illustrated is that vectorization for SIMD is really easy to break. So you need to always check. Don't assume that the compiler is vectorizing everything for you. There are so many gotchas, so many pitfalls, that you really have to keep checking to make sure that you're still getting vectorized non-scalar code. Also mentioned that there are many areas which we're noticing when we're looking at what's assembled, where it would be really nice for the compiler to be using the range information more. About the size of the potential size that values can be. And yeah, mathematical tricks, where one result is iteratively dependent on another one, are not necessarily effective. They may look smart and they may look clever, but when we actually profile them, quite often we find that we have to have a massive increase in speed to beat a SIMD vectorized discrete form. And finally, the modular arithmetic. We can use modular arithmetic to break up difficult calculations in terms of calculations which produce massive intermediate results, which would normally cause numeric overflows. And yep, I think that's it. Actually, thank you.
Yeah, guys, if you have any questions, you can ask us. Oh, yeah.
I have a question, I think, to Evgeniy, to the first part of the talk. You showed us the whole way from top-level code in C++ and down to the CPU architecture. And I'm curious, as I understand, your talk is your experience of optimizing code and creating fast code for games, right?
Okay. Yeah. Basically, because we do care much about performance, but I would say that the same principles, they're applicable. Do you hear me, guys? By the way. Okay. But the same principles are applicable to any high performance, to any kind of field where the high performance is important.
Yeah. So, but my idea that these things are your experience.
Yeah. We did a little bit of research on range, for example.
Okay. So my question is, how do you do this optimization? So you write code, then look into the assembly, and can you describe the process of optimization?
Oh yeah. Okay, I see. Okay, basically the first part is just you just mainly analyzing the code, and the thing is that of course it's not feasible to write the full code in assembly, right? So you just look at the critical parts of your code, or where you have some performance spikes, and there you just analyzing this loop. And what we just tried to show is that you just should be very, very careful with it. Particularly, for example, vectorization, you can use SIMD36 to optimize it manually. So you make sure that the code will be optimized. So yeah, it really, really depends. It just you always bear in mind what platform are you developing for and how this platform works. And bearing this in mind, you just write your code. Yeah.
But having written your code, you check the assembly, which is the
critical parts of code.
Critical parts.
It's not manageable to check assembly of your whole source files. obviously. Yeah.
So, okay, thank you.
Okay.
I have a question to Mark regarding your first example. What is the faster way? The initial vectorized implementation or strip-mined vectorized implementation?
It greatly depends. Sorry. Yeah, sorry. This greatly depends actually on the particular polynomial. We're talking about the polynomial example, yeah?
No, the first one. You said that the polynomial example is not going to be strip-mined at all.
This?
Yes.
Yeah. Okay. It actually is a polynomial. It's x squared. But yeah. It's exactly the same as the later example. If you actually do this, I'll be honest. When I ran results, the SIMD version was actually a lot faster. The SIMD version ran faster.
Okay.
I can't say that across all processors, obviously, because I only just tried it locally to test. But it was something like, I don't know, 2.5 times as fast, I think, something like this.
How many times?
I think it was like 2 or 2.5 times as fast.
Okay.
But obviously the code was much bigger.
And the strip-mined version is not going to be vectorized.
No, sorry. The strip-mined version then became, I think, comparable.
Comparable, not faster.
Yeah. I without. It's comparable because basically it's doing the same. It's effectively producing 4 per loop in the same way that that a vectorized form would do.
Yes, but it has no multiplications.
Sorry.
In a loop, it has no multiplications at all. Why it is not faster?
Oh, well. I'm just trying to look at this now. Hang on. This form, you mean?
Yeah.
Yeah. Well, probably because I don't know. I mean, all I can say when I ran it, I haven't got the figures, but it was comparable. That's all. There wasn't much in it, basically.
Okay.
I mean, yeah, I appreciate what you're saying that the multiplication should vary slightly, but it may just be that the processor that we're running on or something. I don't know. Multiplication does not take that long on the SIMD.
Okay. Thanks.
Hello, thank you for the lecture. I have a small question. Maybe in your company you make research about compilers' performance, different compilers. On the first slide was Microsoft Visual C and GCC. And which kind of compiler produce more effectively machine code? Maybe Intel or Microsoft Visual C or GCC, which machine code usually more effective?
Oh, yeah, it really depends on your case, but usually GCC is much better than Microsoft compiler, but it's only in our experience. So I'm not saying that one compiler is better than another one, but in examples we just showed, usually GCC was like producing better code.
Well, I have a question about strip mining, and if you use this technique, could it lead to, if you use it, then you effectively use 4 times more memory reads than in a sequential version, and can it lead to worse performance?
Well, with what we've done on here, I don't think we were getting 4 times memory reads, no, because we're still only reading everything once.
Yes,
and
but
writing back 4 at a time.
But for example, you have worse latency or worse prefetching and such stuff.
Okay, yeah.
More cache usage.
Yeah, it's a technique.
Okay,
it may or may not, Generally, the improvement that you'll get from strip mining for SIMD is absolutely huge compared to the scalar version. But yeah, it may still be that the discrete form, in some cases, depending on the processor and the actual function used, is still slightly faster, maybe, or slightly slower. You know, you have to evaluate this for your particular function. There isn't a concrete answer to this. You know, but typically we find that, you know, that once we make sure that the compiler is producing SIMD versions of these loops, you know, that the improvement is absolutely massive. It's orders of magnitude compared to the scalar forms.
And maybe a second question. In CPUs, we have to use explicit SIMD instructions or hope for compiler to optimize everything. And maybe, if you know well, for example, in CUDA, we just write a version for each thread is working independently, and then compiler produces our SIMD code. Is there some researches about doing something like that on CPU, because it's really much easier to write?
You mean GPU code?
No. To write CPU SIMD code in a GPU fashion.
I can answer this question.
Go on then.
Yeah, I just mean that. Not sure if the question by itself is correct, because like the GPU and CPU architectures, they're very different. So they're probably, like on GPU, you have really multiple cores which are packed in lanes. And so basically the compiler automatically converts your code and executes it like, it's not really SIMD, it's usually called single instruction, multiple threads. But in CPU, you just have a very, very different architecture. So, yeah.
Yeah, it's very different, but in fact, it's basically the same, because, well, it will be very good if we can basically. Now we need to hope for compiler to vectorize our code, and maybe some guarantees. We just.
Okay, I just think that we ran out of time, so I think we can just move we can move the conversation offline, if that's fine. Yeah, okay, guys, thanks for listening. And yeah, if you have any other questions, just let us know. We are right here.